Hey guys, Greg here. Today I want to talk about a very popular algorithm known as sliding window. Now there's actually two different types of sliding window. The first is going to be called variable length. So basically saying that your window has a variable length, it can change size. And the second method is the opposite. It's just going to be a fixed length sliding window, basically meaning that your window has a fixed size. So you might be told that it's something like size k, where k is equal to 3. So your window is particularly size 3. Now for any sliding window problem, we're generally given either an array or a string. They're basically the same thing, just in a different representation. And if you see in the question, it starts talking about subarrays, or for strings, that would be a substring, then that's a huge giveaway that a sliding window algorithm is something good to try. It might not necessarily be correct, but it's something good to try. So first I'll show you how to solve a variable length sliding window problem, and then after that I'll show you how to solve a fixed length sliding window. And let's solve LeetCode number 3, the third question on LeetCode. Longest substring without repeating characters. So we're given a string s, and we want to find the length of the longest substring. What's a substring? A substring is a contiguous, non-empty sequence of characters within a string. So we want the length of the longest substring without any repeating characters. Okay, so let's look at that in depth here. So the example ABC, ABC, BB, that is going to output 3. Now firstly, let's look at its substrings. So A itself is a substring, AB is a substring, ABC is a substring, all of this stuff is a substring. You could also start at B, and so B is a substring, BC, BCA, those are all substrings. What is not a substring is A, and then C, and then B here. Okay, that is actually something different called a subsequence. So we mean a contiguous and also non-empty sequence of characters. That is a substring. So we want the length of the longest substring without repeating characters, okay? So the length of the longest substring would just be this, except you would need it to not have any duplicate characters. Here, this substring, if you did the whole thing, well, of course, we have multiple B's, multiple A's, multiple C's, and so you need it to have all unique characters in the substring. Now, we'll cover how we actually do this in a moment, but by sliding window, we mean that the window is anything that is between L and R. So right now, the window is just A. It's just L and R on the same spot. If we expand the window, so R is going to expand the window, here our window would be A and B together. If we then contracted the window, it gets smaller, and notice that it's kind of sliding over in general to the right. It's O of N because we're always moving these things over here, so that'll be a linear solution. This would, again, our window would just be here. We could, for example, slide R a few times over. Our window would be between these characters, or equivalently, our substring would be BCAB. And again, we could kind of contract this over. Our substring would then go to CAB. So let's cover exactly how we're going to do this for this problem. Now we know we don't want duplicate characters, so we definitely want a set. You know, if your mind went to like a hash map or a hash set, that's great. If not, that's also okay. But this thing is a constant lookup where we can immediately see, you know, as long as we have all the stuff in here of the characters we've used, we can do a constant lookup and say in O of 1 time, we can say, you know, have we used an A before? You know, I'm saying that we have. It's a constant solution to ever ask if we've used a character before. Okay, so we start them at the beginning here. And for sliding window, you always ask the question, is our window valid? Let's always try to make it valid. What do we mean? Well, in this case, by valid, we mean that we don't have any duplicate characters in the substring. You might have a different problem, and you probably will, where you have some different constraint on why it's valid. But here the question is, do we have any duplicate characters? Well, we have no characters so far, so our window is valid. We will add R's character, which happens to be the same as L's character here, into the set. So we'll say, okay, we add this into the set, and we have no duplicate characters. So we've actually seen something so far. We'll keep track of our longest length that we've seen. We only care about the longest length, not the actual substring. Probably we would have initialized this to be 0 at the beginning, but now it's been updated to 1. So far, you know, we've seen a substring, which is just this, which is valid. There's no duplicate characters, and so we should record that length. Now, while our window is valid, we want to expand this over because we want to try and get the longest length here. We're looking for the longest one. Now we moved R over here. Is our window still valid? So this substring, is this still valid? Well, yes, it is, because if we were to ask if, if this is S here, if we asked if S at R, aka just this character right here, is this in the set already? Well, no, it's not. So we're going to put that into the set, and then we have a length of 2, because this is still still valid, so we should update that. We'll say our longest length that we've seen so far is 2. Let's try to keep this going as long as we can. We move R over, that expands our window. Is S at R, aka this character, is that in the set already? No, it's not, so this is again valid, and so we have a length of 3. By the way, how do we actually calculate the length? Well, we could calculate the length of our set, but in general, that's not as versatile a solution because we might not always have a set. So our window length, the current window length, is always going to be, I'll call it W. That is actually just equal to R, yes, the indice values, R minus L plus 1. Why is that the case? Well, here we want the distance between them, which is 2, but then we also want to add 1 because we want inclusive of the characters. And that will make even more sense where at the beginning, this is not a window length of 0. We are looking at a character here. So here, this would actually plug in that we'd have 0 minus 0. You wouldn't want this to be a window length of 0. You'd want to add 1 so that this is a window length of 1. Okay, so with this formula, we can always use this formula to calculate, given any L and R wherever they're located, you can always calculate the length of the current window with that formula. Okay, but just placing this back to what it was before, we had R over here. We saw a longest length of 3, and we have these 3 characters in the set. Now we'll try to find a bigger one again, but we run into an issue. If we ask if S at R, aka this character, if S at R is in the set, yes, it actually is. Okay, that means that the current substring we're looking at is invalid. It's invalid, so we are not going to update this because what we have here is actually a failure. You want to move L over to start to make the window valid. We want it to be valid at all times. When it's valid, we move over R. When it's invalid, we move over L. Now, if you were just to blindly move L over here, well, that's not going to ever fix the problem because you'd again ask, hey, is this character in the set? Well, yes, it is in the set, and it's always going to be in the set because you didn't remove it over here. So before we move L over, you have to remove S at L, aka this character, from the set. So the window is invalid. Let's move over L. We ask again here, hey, is this valid? Okay, this might be valid. Did this fix the problem? This might have fixed the problem, but it also might not have fixed the problem. Is S at R in the set? No, it's not. Okay, so that did fix the issue. This is again a valid substring. We add A back into the set because we're adding it from S at R. And you could again, if you wanted, you could say, okay, well, did we find a better maximum? No, we didn't. We have a current substring of 3. We already actually had a substring of 3, but you could calculate that if you wanted to. And then this current window is valid. When it's valid, we move R over. And so then again, we encounter the same issue. We ask, is S at R in the set? Yes, it is. That means we have a duplicate character. This is an invalid substring. Let's make it valid. Before we move L over, we have to take this out here. So we take out S at L from the set. We move this over. Is this valid again? Yes, it is. If you wanted, you could say, okay, well, I found another 3. That's great. It's not going to help, but that's fine. We have a valid substring. We would add S at R back into the set, and then we could say if we wanted again, okay, we found another 3, that's great. We have a valid substring, so we actually move R over here. Now again, we encounter the same issue. Here, we would want to remove S at L from the set. We move this over. We would want to add S at R back into the set. This is a valid substring. I'm going to move a little bit faster now. So we go to the right over here once. Is S at R in the set? Yes, it is. But here, this is the first time we've seen that this actually doesn't fix the issue right away. We have to take away this character, but that did not solve the problem because B is still in the set. S at R is still in the set. So we try to fix the problem. We go over here. We remove that, and now this is a valid substring. We put B or S at R back into the set. We can move R over. We run into an issue again. We remove S at L, and we move this over. We still have an issue, so we move this over here. And then at the very end here, they're equal to each other. We'd actually end up adding S at R or B back into the set. And when R gets to the end here, that is when we'd complete the loop. Okay, so let's write this code. We want L to be initialized at 0, and you might expect me to set R to be 0, and I kind of implicitly will in a moment, but we're going to end up sending R through a for loop, and we're actually going to have a for loop and then a while loop inside of that. Sounds like n squared. It's not. We'll see it in a second. So we have L as 0, and we'll set the longest equal to 0 as well. That's saying so far the longest length we found is nothing really, and we're going to have a set that keeps track of duplicates. So set set is just an empty set, and we'll also get n is equal to the length of our string. Now what we want to do is for r in the range of n. And in your mind, I certainly wouldn't blame you if you implemented that as a while loop. And we're going to do a while loop in a second, but you'd actually want r through a for loop. And that makes sense because this has got to be a linear solution here. Okay, the point of this is that all of this stuff is going to be just O of n coming from this loop right here. We just have to make sure in here that the window is valid. And that's what we do right here, is this is basically going to say while it's invalid. It's invalid while s at r is in the set. Okay, so it's basically saying we're trying to add this new character on the right into the set, but while it's already in there, that means our current window is invalid. So we fix it exactly like we said. It's just two steps, the set.remove of s at l, and we haven't actually added anything into it yet, but we will in a second. So we remove s at l from the set, and then we just move on. And so L is going to go up by 1. So this is your loop that says while our window is invalid, while we're looking at an invalid substring, invalid in this case, meaning we have duplicate characters, implying that you're unable to just add s at r in the set because it's already there. After we get out of here, this is where we have a valid window. What's the length of our window? Well, I'll call it W is equal to r minus L plus 1. We already did that formula. Then we want to set longest, which is going to be our return value. We'll set longest to be the maximum of what it was before and our current window. We want it to be the maximum of itself and the new window length. So if we found a better window length, we want to use that. If we didn't, then we just want to use the old value. Okay, and then at this step, we want to make sure that we actually add into the set s at r. We know at this point, if we're adding it, s at r wasn't already in the set because we have this running while we do have it in the set, meaning we had a duplicate. And after this, we just want to return the longest value that we saw. Okay, so let's really break down what's happening here. Well, you might have been taught that when you have nested loops, that's going to be O of n squared, but it's not that simple. This loop, it's very clearly O of n. Like unless you had some clever breaking thing in here, this is definitely just an O of n thing to do. This one, well, that's saying we're gonna remove characters from the set. Well, what did we actually add to the set? At most, you can say we've added all of the n characters into the set. So if this is always going to remove a character from the set, that's also going to run at most n times. And really all it's doing is forcing L to move forward. So this is basically going to be O of n as well. Okay, so the overall time complexity of this algorithm, this is going to be a big O of n solution. And the space complexity here, in this case, it's also going to be big O of n. That's not always the case. A sliding window algorithm in general is a constant space solution, but because to check if the window is valid, we actually have to use a set for this problem. So the space is also going to be O of n. Let's solve maximum average subarray, leak code number 643. It's a great fixed length sliding window problem. So we're given an integer array of nums, and that has n elements. And we're also given an integer k. We need to find a contiguous subarray whose length is equal to k that has the maximum average value and return this value. So this example here, we have this array of numbers and we have k equals 4. So we need to look at contiguous subarrays of length 4. So the first one would be this, 1, 12, -5, and -6. The second would be moved over 1 like this, and the third one would be this. Each of those three things would have an average, and we would take the maximum average, which happens to be 12.75. That is given by the second one with 12 minus 5 minus 6 and 50. So using this window right here, that would create the maximum average of those three, and we would return that value. And then they have some really silly example here. If k is equal to 1 and you have just one number, well, the average is just 5. So since k is equal to 4, that is a defined window length for us, where we are going to use a fixed length sliding window. So as we saw, we want to look at this subarray, or this window, and so we'd have these four numbers. We would then move it over and look at these four numbers, move it over to the end, these four numbers. Those are our three different windows, or our three different subarrays. We'd look at each of those averages and pick the best one. Okay, so first we have to build up this window because it doesn't really exist yet. We need to build it up to this point, and then from there we can start sliding it over. So we'd want to hold two things. One would be the maximum average, because the max average is the thing we're looking for. Right now we'll just set this to -infinity because we don't have any yet, and anything we find will obviously be bigger than that value. And we'd also keep track of our current sum. So that's going to be the sum of our current window, or our current subarray that we're looking at here. And the current sum so so far is 0 because we don't have any numbers. And the first thing we would do is start to build up this window. So for that, we would do a loop that goes over these indices. So we'll get I, that's going to start at 0 to look at the first number. So what that does here is we simply just increase our cursum. So that is going to go up by 1. We're starting to build up this window. So now we have this. We need to move this over to be 1. And so that will slide it over here. Our current sum of this window is now the sum of these two. It's going to go up by the value of this. And so it's 1 plus 12. That is going to make it 13. We're going to slide this even further. And so we set this to be 2. That is going to add this in here. That actually loses value. So now we actually go down to 8. We're going to slide this a little further. The last one here, this is going to set I equal to 3. And so we look at this number. That is going to take away 6. So now the current sum is 2. So we have 1 plus 12 is 13, minus 5 is 8, minus 6 is 2. So this is the current sum of our window. So we have a window right now. Before we start sliding this thing over, we need to actually keep track of the current average. And so the current average is simply just 2 divided by k, because k is always going to be the length of our window. So if you do 2 over k, which is going to be 2 over 4, well, we are keeping decimal numbers. So this is basically 0.5. So that is our average so far. So that's the average of our first window. And now let's start sliding this over. Now, when we slide it over, we are going to start at the next index, which in this case would be 4. So we're going to move this over here. Notice that we are adding a value. If we add a value, we should add that number to it. And so we'd add 50, which makes 52. And if we slide it over, so we add what's on the right and we lose what's on the left here. So we actually need to subtract that. We need to subtract this value. And so we lose 1 to get 51. And now we have a new window. And so we can calculate a new max average. It's going to be 51 divided by 4. After calculating, it turns out to be the value of 12.75. Okay, so that is our max average so far. The reason we updated that is because that value, we're looking for the max average. And so we plug that in there. Now we slide this over again. We'll move to the last index that goes over here. So we add 1 right here, we lose what's over here. So we're going to add the 3, so we get up to 54, and then we subtract what we lost 12 here. We are now at 42, and 42 over 4, that is going to give a value of 10.5. So we actually don't update that because that was smaller than our old one. Okay, we want the max average, so we are happy with the one that we had there. We're happy with 12.75. We actually get to the end here. We know that because our index is at the end of the array, and we would return the max average that we have. Okay, so we're almost good to go here, but I just want to show one particular thing to make sure it makes sense, is that when we are sliding the window, say that we're here, when we slide the window, the thing that we're adding, so we're going to do a cursum plus equals because it's going to increase the value of nums at I. If I copy this here, we would actually have cursum is going to minus equal, it's going to lose the value of nums at I minus k, because check it out. If I is here, this is the value of, well, it's 0, 1, 2, 3, 4. K is 4, and I is also 4 here. So the first thing we should lose is the first number. Well, we should lose index 0. And so we would lose 4 minus 4. And so we'd lose I minus k, which is going to be 4 minus 4. We would lose the number at index 0. And so that's why we do decrease by the value of nums at I minus k. And as we slide this over here, that is always going to be what we're losing. Okay, so we're going to get n is equal to the length of the nums array, and we'll specify that our current sum is initialized at 0. Now we'll start to build up our window. So for that, we'll do for I in the range of k. This is going to run k times, where the indices are 0 to k minus 1. So we are building up the window. We will do cursum is going to go up by nums at I. So this simply just builds up the initial window. Now we can initialize max average to be the only average that we've seen, the average of the initial window, which is cursum divided by k. So whatever average that is, that's the best one we've seen so far. Now what we need to do is for I in the range of k to n. Okay, so we do that, which is going to start at inclusive index k. That's good because we left off at basically k minus 1 because this is exclusive. So here we went from 0 to k minus 1 to build it up. Now we start at the next index, which is k, and we're going to go up until n minus 1, which is the end of the string. So when we move it to the right, we're going to get a value. Cursum is going to go up by the value of nums at I, but we also are going to lose the value to the left. So cursum is going to go down by the value of nums at I minus k. Okay, so from there we can calculate the average of the current window, which is cur_sum over k, and we'll get max average is going to be the maximum of itself, max average, as well as the current average. Okay, if our current average was bigger, then we'll set it to be that. Otherwise, if our original was bigger, then we'll just use what it was before. Okay, after we've done that, we have now built up the window and then we've slid it across to get the max average that we saw. From here, we can simply just return the max average. Okay, so the time complexity of this is a big O of n solution. Why is that? Well, basically we just do in two different pieces. We're going to slide across the nums array. All of the stuff we do in here is all constant operations. So really we're just going across the array. And so that is definitely going to be big O of n. And storing, well, storage, we're not really storing anything. So this is going to be a constant space solution. Okay, here's our code. I hope this was helpful, guys. Drop a like if it was, and have a great day. Bye-bye.